Hello everyone. And I'm recording, okay. How is everyone doing? Good. Anything exciting for the weekend plan? Nobody? Just going to study carbon compounds and watch the lectures again. Okay, so to save all of us some time, I provided some slides. So I posted a PowerPoint slide on Canvas yesterday. So that is a slide that the publisher provided for the instructors. And I looked at it and I think it's really useful, but I'm going to exactly follow the book. Sometimes it wasn't quite aligned with the book. All the materials eventually you should know, but I thought that it's better that I just provide my own slides. But I posted that because I thought it's really useful. So when I'm teaching you, and after I finish with the chapter, if you don't understand anything from the PowerPoint, let me know. Does that make sense? But I want to just follow the book as it is, and I thought it's just better that I have like customized slides. Okay, and something that I forgot to mention in the last session, the same thing that I said about my accent, if you don't understand, just let me know or ask for clarification. The same thing with handwriting. If you cannot read something that I'm writing or something is unclear, just ask me. So just don't let it go or like stop caring, if that makes sense. So, because easily I can just explain that to you. So I emphasize that get the textbook and you have the e-text available whether on the publisher CHEM275 website or through University of Idaho bookstore. But I need you to have it because yesterday as I was preparing for the lecture, I was just like writing some notes for the things that you study. And I realized literally, and you see from my notes too, literally is word by word from the book. And it saves us all so much time if we just like study the sections and you understand much better, believe me. And as I said, I will tell you explicitly which sections I'm teaching, and I ask you to read those sections. And then if you have any questions, let me know. So you are required to have the book and read the sections. And something that I forgot again mentioned last session, you can just call me Lida, but you're welcome to call me Dr. Farsi, Professor Farsi, anything you like. So, but you can just call me Lida. So don't worry about that. And I already told you that I have the PowerPoints uploaded, and the reason I'm going to post this PowerPoint from today's lecture and all the lectures after the class, because I'm going to add things as I teach to them, and I don't want to have like several PowerPoints, so as less as possible. So that's why I upload these after each lecture. And also, since I'm going to post everything online, I don't want you to worry about taking notes. I was a note taker myself and I wanted to write everything. So if that's your learning style, that is fine. But don't stress out about writing things because I'm going to post everything online. So just like focus on learning. Any question about anything so far? Good? Okay. So what is carbon compounds? Do you have any idea what this course is going to be about? And you can also read and then answer. And the other thing that I was thinking last night when I was preparing for the lecture, I thought that it's really good. As I told you, attendance is required unless you are sick, which I ask you to stay home, and your absence is excused, so don't worry about it. And I decided, as I said, I'm going to, call some names and then make note of attendance, but I decided to do that after I progress with the lecture, maybe in the middle of the class, so it would be a break for all of you too, after I talk for some time. And I was thinking it's really good to have class participation to kind of, because last session, as I'm talking, I realize I'm just standing here talking, the class may get boring. So I think if we have class participation, the class would be more dynamic, and then probably you learn more, and then you don't fall asleep. So, and I really encourage class participation, and by the time goes by, I know who are participating, and if you're worried about it, or you want me to know that, okay, I answered this question during the class, you can also email me. But all these things being said, if you get like 898, or like, out of 100, at the end of the class, 88, and then you want to get an A, I look at the name, and then I realize you had class participation, I easily give you an A. Does that make sense? So in that way, I want to encourage class participation, and you don't have to answer any question right, as long as you participate in the class. Does that make sense? Okay, so this course is basically just organic chemistry. And previously, organic chemistry, it was a branch of science explicitly dealing with like living things, like like plants, or like human beings, or like animals. Like, as you can see, organic chemistry, it has like the word of like, it comes from like organism, or like organ, right? So previously it was just like limited to that. But right now, there are like scientists going to the laboratories, and then they making things, so they have like synthetic compounds that those contain carbon materials, and now we consider those, organic materials too. So now this is like the more general definition of organic chemistry. So, compounds from nature, and also synthetic compounds. And in a nutshell, it's like carbon compounds. So compounds that they contain carbon. Any question? So I just wanted you to know that this is like the general scheme of the book, what you are dealing with, or we are dealing with rather, in this course. And I start with chapter 1. And as I said, I explicitly tell you that which part I'm going to teach. So, so it's the first page here before we start like section 1.1. It just like gives you an overview of like the chapter, which is like bonding and isomerism. And I'm going to talk more about isomers as we progress with the chapter. But I thought this is like really good motivation that why we are studying this chapter, so that's why I included this very first page. So here we have like 2 different compounds, and as you can see, both of them have carbon, right, as part of them. And the chemical formula, so is there anyone that doesn't know what is a chemical formula? Is it crystal clear? So if, when I'm teaching, this session would be mostly review of like Chem 101, and also, if you didn't take that course, any elementary chemistry course that you learned previously. So if something that I'm teaching and you don't remember what it was, don't be afraid to ask. Okay? So just let me know that, okay, I don't remember what is compound. Can you just explain it? So don't be afraid to ask. So as you can see, these 2 have like the same chemical formula. And one of them smells like apples, the other one smells like pears. And they have like the same chemical structure. I mean, the chemical formula is the same. So just looking at the chemical structure, can you see any difference between these 2? What is it?
The place of the oxygen in the
What is it?
The arrangement.
Exactly. So you see here, we have like these carbon carbon that is bound to oxygen, you see? And here, so you have like one CH3 group here, and then you have like CH3 group here. So you see that this COO here and here, in this one, we have like carbon bonded with oxygen, and then here to carbon. And don't be scared about the chemical structures. We're going to talk about this throughout the course. But because of this small difference, these two are like different compounds with different properties. So basically, the different properties are because of different chemical bonding. And then later on in the chapter, I'll tell you that when we have like the same chemical formulas but different structures, we call these compounds, or like these two molecules, we call them isomers. And then the same thing, about like, if you consider like table sugar and table salt, they have like extremely different melting points. Or like if you think about like different properties of different materials, like, why some materials are like water, or like the states of different materials are not some materials are water, or like some of them are liquid, some of them are gas. So all these different properties are because of how different atoms bond together. So this is the main aim of this slide, to tell you that because how atoms bond together, we can have different properties to it here. So we had like here this CH3 group here, and then I teach you later on that what we call them. And then here we, it was attached to carbon. Now it was attached, for like methyl butyrate, it's attached to oxygen. And then we deal with chemical bonding and the number of, and as you may remember, these dashes or lines here, these are like chemical bonds. So these are like, each of these are like 2 electrons, right? So these are really important to know. These are like the basics, to know how to write electron configurations for like each element and compounds, and how to basically draw Lewis structures, because this is basically what we're dealing in this course. So if you have, again, any questions, or like you don't remember, or that you're not sure, or maybe the terminology that I'm using is different from what you used to, so just email me, and I provide you with resources to watch, or like I schedule Zoom meetings with you, or like you can stop by my office hours. So maybe what I'm trying to emphasize is that these are like the, building block, or like atoms, if you will, of our course. These are really important things. So make sure. And here, I guess I start using the highlighter here. I guess that would be more effective. So people that watching the lectures, they can also see what I'm pointing at. So bonding is the key to the structure, physical properties, and chemical behavior of different kinds of matter. So as we said, they can have like different smells. This is like a physical property. They can have like different chemical behaviors, and they can have like different structure. Any question about bonding? Okay, so now explicitly, as I said, I'm going to tell you which section I'm teaching, so you have the chance to go read it carefully. So now I'm talking about I'm teaching section 1.1, which is like how electrons are arranged in atoms. And here, to find the answers to this question, some of them I'm going to write, but in general, if we just read the chapter, and also you can refer to the PowerPoints that I posted on Canvas too, we can find the answers. So can anyone tell me what is an atom? Anyone? Yes?
Type of particle.
They are type of particle, yeah. But what is it specific about them? So what is the difference between H2O, water, right? Or like, what is, so is this an atom? This piece of paper, is it an atom? So what is an atom?
It's like the smallest building block ever.
Exactly. So all matter, they consist of atoms. And they are like the smallest part of the matter that they have the same chemical properties, right? And do you remember the periodic table? And then you have like these two nice periodic table. I was teaching at JEB last semester, and it wasn't a chemistry building, so they didn't have a periodic table, and it was bothering me. But now we have like very ran through, so we have the periodic table. So do you remember these elements, right? So all of them, if you have like just like, and then one, if you just consider, I mean, we know that oxygen is a diatomic molecule, so it has like we have like O2. So we have like 2 oxygen atoms in one molecule. But for instance, if you have like sodium, most metals, they are just like, I mean, most of them, not all of them. We have like just 1 sodium atom, right? And if we have like sodium, and then we go to the laboratory, and then we try to have like the smallest building block, as your friend mentioned, to have the same chemical properties, we call that a sodium atom. Does that make sense? Okay. So now, what do atoms contain? If you remember from like your elementary chemistry course, there were like scientists like Democritus or like Luciferus, like ancient Greek philosophers, and also after they said that they believe that atoms, they cannot be divided to simpler or like a constituents. They don't have anything else, so either like indestructible, right? They don't contain any other particles. And then John Dalton said the same thing, and afterwards like Thomson realized that that's not the case, and atoms contain of other constituents. Do you remember what they are?
So like your protons and electrons?
Yes.
Protons, electrons, and neutrons.
Exactly, right? And do you remember what are or first of all, if I want to draw an atom, how do I put protons, neutrons, and electrons? Where do I put them? Can anyone remember?
Like the protons and neutrons are like in the middle, and then the electrons are on the outside.
Yes. So we have like a nucleus right here, and which contain protons and neutrons, right? And then we have like electrons, around them, or and then we had like different theories, and then I put like here electrons, and we had like the nucleus. If you can read what I wrote, nucleus. And then protons and neutrons are really small portion of the atom, but they are heaviest. Do you remember? And we had electrons around them that take the most volume, and they are really, really light. And I don't expect you, when you go to look at the PowerPoint, it has numbers. I don't expect you to know the numbers, but I expect you to know that electrons are really light, but protons and neutrons are really heavy, and they are like in the center. So, can anyone tell me what are their charges? Yes?
Protons are positive. Protons are positive, electrons are negative, and then neutrons are neutral charge.
Exactly. And can anyone tell me what is the exact numbers? So like protons are like positive, neutrons, they don't have any charge, and electrons are negative. But how much negative charge does one? Exactly. So protons are like, each one proton has a charge of +1, one electron has -1, and the neutrons, they are neutral. They don't have any charge, they are 0. And which one is the lightest, based on what I just said? Exactly. And what is an atomic number? Can anyone remember what it was?
Number of protons.
Exactly.
What?
So number of protons, right? And then if you look at the periodic table, where do you see that, these numbers?
The top right.
Exactly. So you see, for instance, for nickel, Ni, can anyone just look at the periodic table, that you have like on the walls and tell me what is atomic number for nickel, Ni? What is it?
28.
Is it clear for everyone how we read that number? So you see that you just, I have the luxury to walk during the class. So here in nickel, we see that number 28. Probably now people cannot hear me there, but yeah, we just like look at the top of the element in periodic table, and here we talked about nickel, and then we read this number here, that is 28. What is atomic weight? Anyone remember?
Like on the periodic table?
The weight of an element, yes. And what did you say?
Like what number it's on the periodic table? Is that what you're asking?
Yes, so that is like the number written on the
On
below
the bottom.
each element. And atomic mass and atomic weight, and like they are like roughly the, so atomic mass, or like mass number rather, is the number of protons and neutrons. And that number, because we have like atomic mass unit, scientists define that in a way that for proton, that number is roughly 1, so it's like 1.00, and then if you go to the PowerPoint, you see the exact number. But it's roughly 1. So basically, the atomic weight is roughly the number of protons plus number of neutrons in an atom. Does that make sense? But it's basically the weight of that atom. And as we said, that's because the electrons are really light, so we can't just like neglect that when we're reporting atomic weight. Does that make sense? So in nutshell, it's number of protons plus number of neutrons. And do you remember from previous years or like last semester that which atom constituent is important when we talk about chemical bonding?
Electrons.
Exactly. Because when we have like an atom here, as I like depicted, we have like protons and neutrons in nucleus, and they won't participate in reactions. Except nuclear reactions, which is like out of scope of what we're dealing with in this course. So for the sake of our course, carbon compounds, we deal with like electrons, and as I progress with this lecture, we realize that we deal with valence electrons, which are like electrons in the outermost shell in each atom. But in general, electrons are involved in chemical bonding. Okay. Any questions so far? Good? Okay. You remember when we talked about like how can I do this more effectively, I guess. When we talked about like the, atom constituents and how they are placed in an atom, there were like different theories with the time that scientists came up with, and the most popular ones were like Bohr model. With the popular I mean closest to the reality. Was like at first Niels Bohr recommended and came up with this theory that we have like nucleus and we had like orbits around nuclei or like nucleus in an atom, right? And then they were like how we have like in solar system we have like sun, and then different planets are like orbiting around it. He was saying that it's similar concept. And I don't go in much more detail to them because I just want to go back to what we are dealing with in carbon compounds, but just like email me or like ask me any questions if you want to know more about these theories. And afterwards, we had like the quantum mechanical model, that scientists realized that, and they were doing experiments, they realized that they cannot explain some phenomena in laboratory, and they realized that we don't exactly have electrons in orbits around nucleus. And they proposed the concept of orbitals. An orbital is the probability of electron existing around around the nucleus in like certain locations. For instance, here, previously, Bohr said that if you have like nucleus here, we have like orbits. And for instance, for like lithium, the atomic number is 3, which means the number of protons are 3, which means number of electrons are 3, because lithium as itself, it doesn't have a charge. And then he said that, okay, we have like 2 electrons in the first orbit, and then we have like 1 electron, and these are like circle. I apologize for the crooked drawing. But here we have like 2 electrons in the first orbit, and then 1 in the second. But so these are like orbits. But what orbital means is that I cannot exactly locate this electron here. I don't know. The electron can be here or here or here or here. It can be like around the atom, but we don't know exactly where. But we call this probability of electron being in certain location around nucleus orbital. And it's kind of like difficult to visualize. But as you remember, we had like different orbitals that we denote that with a letter and a number. And the letter was telling us which orbit or which shell we are dealing with, like n equal 1, n equal 2. Does these things sound familiar? And then we had like different letters, like s orbitals. Can anyone remember what was the shape of s orbitals? Anyone? Yes, they are spherical, right? And then we had like p orbitals, they were dumbbell-like, And as I said, if these things seem so unfamiliar, after reading the chapter, if you have more questions, just like, email me. I can also send you the links to the Chem 101, so you can just listen to the lecture, or like online resources, I can guide you, So if you don't remember these things, don't be afraid, just like email me. Keep referring to that, So for instance, for lithium, what is the number of valence electrons?
1.
Exactly, because you just see in the outermost shell, you see 1 electron. This electron here, because I just highlighted with some other color, this electron, we call this valence electron. So we call nucleus and electrons that are not valence electrons or like inner electrons, we call them kernel, right? So this is just the terminology that we use. And when we write Lewis structures of different elements, for instance, for lithium, we just write here lithium, and then we put like, it has like 2 what?
Would it be 2 kernels?
Exactly. So we have like 2 kernel, and then when we write the Lewis structures, we just write, lithium with valence electrons, right? So we write this and then put a dot here, do you remember? And when we write lithium, that is kernel. Basically, the nucleus and inner electrons, or like non-valence electrons. So it's just a term that we use. But now, can anyone tell me what are orbitals? Anyone remembers?
It's what the electrons are in.
Yes. So just go back really quickly to the previous slide. Okay, so this is orbital. And what are shells? As I just mentioned, we have like these different orbits, or like that we call like different shells. And then these are like the principal quantum number n. So these are like different shells. Yeah, I don't know whether I should like close this first or like have my mask off first. Anyway, so what are valence electrons? As you can see, these, at least this session is mostly a review of the things that you knew previously. But if you don't remember any of this, and after reading the chapter, still you have problems with any part, just let me know. So anyone can tell me what are valence electrons?
Electrons on the outer shell.
Okay, yes, yeah.
The outermost shell of electrons.
Exactly. So these shells that I just depicted in the previous slide, so this is like valence electrons are the number of electrons in the outermost shells, or we call those valence electrons. And what is kernel? I know as a fact I didn't use this term last semester, but can anyone from that had like the course previously with someone else, anyone remember what is kernel? So you see how here we call, okay, and we know what is kernel. And electron configuration. This is really important to know how to write electron configurations and how to draw Lewis structures, because basically in this course, in almost all the chapters, we deal with how atoms bond together to have like different, to form different compounds, and then depending, as I showed you in the first slide, let me just remember how to write electron configurations. And as we mentioned, we have like different orbitals. And if you remember, as I mentioned, we had like a letter and a number, for instance, 1s, 2s, right? 1s, 2s, 2p. And then can anyone tell me what are these, superscripts here? Like this 1, 2, 2, 1. Do you remember what do they represent?
Electrons.
Exactly. And do you remember that each orbital can have maximum, we had like s orbitals, and this was like the orbital diagram, right? So, and these were like p orbitals, right? Or p subshell, and then each of these can have maximum 2 electrons. Do you remember? So like p orbitals, and then I guess that was like bad practice. Let me paraphrase that, or like write that again. And then when we wanted, do you remember like the Pauli exclusion principle and Hans rule? Right? Anyone remembers those? So what was Pauli exclusion principle?
Yes, that you have to have one electron in each box before you double them up?
Yes, that is Hans rule,
Oh.
but yes, basically these two things I want you to remember. So Pauli exclusion principle was telling that in each of these blocks, we can have maximum 2 electrons with opposite spin. And Hans rule, it was just like bad of me to, I just like put them both. I was like, which one was which? So yeah, as long as you know the rules, you're fine. In this course, I don't ask you which one was which. But in Hans rule, we were saying that first, you put these blocks or orbitals singly, and then we pair them up, right? But at the end of the day, you can have 2 electrons maximum in s orbitals and 6 electrons maximum in p orbitals. And then the same thing with d orbitals, that you can have like maximum 10, and then with f orbitals, maximum 14. Do you remember? Okay, so, but this is the thing I need you to know, that 1s2, 2s2, 2p6, that's 2p6 is maximum number of electrons. And in the next one, and you have like these tables, table 1, 1, table 1, 2, table 1, 3, that you can just like go back and then review these concepts, and then you have like the electron configuration for like the first 18 elements, and I asked you to just read those to refresh your memory. And here, as an example, we want to write electron configuration for carbon. So if I just ask you here, write electron configuration for carbon, what is the first thing you do?
Atomic number.
What's that?
Atomic number.
Exactly. You look up atomic number, and then you go to periodic table, and here I just like included that here, and then you see that the atomic number for carbon is 6, right? And you start writing 1s2, and as we said, like we have like one number, one letter, and the maximum number of electrons for s orbitals can be 2. And then you write 2s2 and 2p2. And if you remember, if you are in n equal 2, meaning the letter is 2, right here, the coefficient in a sense, here, if it's 2, you will be having 2 types of orbitals, p orbital, s orbitals, and p orbitals. And if n equals 3, you will be having s, p, d. So this is a way to remember, right? Does that clear what I just said? So here, if there is like, you know, and I guess I highlight this by yellow, if like n equals 4, how many subshells we'll be having? Or like how many orbital types do we have if n equals 4? Is that clear what I'm saying? So if n equals 1, we'll be only having one type of orbitals, s orbitals. If n equals 2, we'll be having 2 types of orbitals, s and p. If n equals 3, we'll be having 3 types, right, s, p, d. So what about if n equals 4? How many type of orbitals we'll be having? Exactly. And here you see that for 4, we have like 4s, 4p, 4d, and 4f. So in that way, you'll remember how to write these things. Anyway, so if I ask you to write that for chlorine, right? You say 1. Okay, and n equals 1, we only will be having s orbital. So we write 1s2. And then we count the number of electrons. 2. Is it 17 yet? No. So we continue writing, right? So we write like 2s2, it can have maximum 2 electrons, and then 2p6. And this is like we only have s and p. And then we count the number of electrons. 2 plus 2 is 4, plus 6 is 10, right? And then, so it's still not 17. So we progress with like 3s2 and then 3p, and then here is 12. So we only need 5 more to become 17. I was telling last semester to students who had like Chem 101 to just like remember this, and then at the time I just told them that I needed them to know like this much for their exam. But obviously now I expect you to be able to write all of this, you know, and I don't give you an element in periodic table that has like, you know, 103 electrons, for instance, or like 112, you know, and then in the periodic table there, you know, you can also see like the atomic numbers, and as you can see, we have like till, you know, 118 elements, and some of the elements are still not known. And if you go to the periodic table, you see that, I mean, they didn't even, in this book, we don't even see like after 112. It's just like until 112, but over there, if you look at some periodic tables, after 112, between 100 and 112, I mean atom with atomic number of 112 and 118, there are like elements that are like not discovered yet, but they know what their electron configuration would look like. Anyway, all of these things being said, this is how you fill the orbitals. And if you remember, we fill out orbitals with the ones that have lowest energy. So 1s has lower energy than 2s, 2s has lower energy than 2p, and so on and so forth. And if you count the number of electrons in the first shell, n equals 1, it would be maximum 2 electrons. I guess I use the highlighter again. I guess I use, I don't know, red. It would be 2. Or like if n equals 2, the maximum number of electrons, 2 plus 6, would be 8. And then if I do the same for like n equals 3, would be 18. And then for n equals 4, would be 32. And then so on and so forth. And then here you can see the maximum number of electrons in each shell. And these are, as you progress with the lecture and the book, you realize why these things are really important to know. That the n equals 1 can have maximum 2 electrons, and this is the reason. N equals 2 can have maximum 8 electrons. Does that make sense? Okay, any questions so far? Okay, so to give you guys some break, so let's do some attendance. And I want to know you guys better, and I'm pretty sure we don't have 60 students present in the class. And there were like maybe like 3 people that emailed me. So, okay, where is Taylor? Okay, where is Mandy? Okay, I kind of like remember the elementary school. And I don't want you guys to feel like, I don't know, what is the word? I don't want you to feel like that you're sitting on an elementary class, But as I told you, I had really tough time last semester, and I want you all to succeed. Jessica? Okay. Grant? David? Lily? Okay, cool. Both of you. Good. Lola? Okay. It's just interesting. Anyone that I'm just like calling on people who are present. Julian? Okay. Sierra? Brayden? Kyle? Okay. Can you raise your hands again? Okay. Tanner?
Yep.
Shelby? Little? Ashley? Ashley? Kate? Natalie? Natalie's not here? Zach? Okay, I think that's good for now. Okay, any questions so far? And I'm progressing much slower than I anticipated. But hopefully I can. I guess, as I told you, I try my best to cover everything in the book, but I suspect most probably I cannot. So that's why I specify exactly where I'm, which part of the book I'm teaching, so you know exactly what study. So now I'm going to, that was a really bad idea. Okay, now I'm going to talk about ionic and covalent bonding. And as I said, I'm going to even, that's why I'm posting these things after the lecture, so I make sure I include everything. So you don't have to worry about taking notes, but you're welcome to. I'll post everything. So can anyone tell me what is ionic bond, an ionic bond, and what is covalent bond? What is the difference?
Ionic is a non-metal and a metal.
Okay.
And then covalent is 2 metals.
Not metals, so 2 non-metals. Yes. And in general, so the definition is correct most of the time. But I was telling, students previously last semester too, that most of the time when we have a metal and non-metal, we have an ionic bond. But we may have ionic bond and we don't have any metal. So we may have ammonium, for instance, NH4 plus, this cation, and then with OH minus, this anion, and then they form NH4OH. This is still an ionic compound, but it doesn't have a metal. But in general, when we talk about ionic and covalent bonding, when we talk about these types of bonding, we deal with, as I said, when we talk about chemical bonds, we're dealing with electrons, right? So protons or neutrons, they don't participate in chemical bondings. And when we said we have an ionic bond, we mean that electrons between atoms are being transferred. So for instance, if I have sodium and then chlorine, right? As of themselves, they don't have any charge or neutral. But if they want to form a bond, sodium loses an electron, chlorine gains an electron, and then we have Na plus, Cl minus, and they transfer the electrons by sodium losing the electron and chlorine gaining an electron. So when electrons are being transferred, we call that ionic bonding. Does that make sense? But in covalent bonds, electrons are not being transferred. They are being shared. And to give you a better idea, I'm going to talk about table 1.3, which is that one is in section 1.1. So if you want to write electron configuration, or not electron configuration, electron configuration was 1s1, 1s2, 2s1, that thing is electron configuration. But if you want to write Lewis structure of sodium, for instance, can anyone tell me, I told you that we have the kernel, which is the atom, basically the nucleus and inner electrons, right? So we depict the valence electrons. For sodium, it's in group 1A, right? And if you go look at the periodic table and then group 1A, do you remember that what was the number of electrons? So if I ask you what is the number of valence electrons for nitrogen, how can you tell me that? Or I guess, let me go back to previous PowerPoint that I have here. Okay, let me go to this one, for instance. Okay, here we have a periodic table. So if I ask you, what is the number of valence electrons for nitrogen, can anyone just look at this table and tell me what it is? 5. And the simple way is that to just look at the group number here, nitrogen is in group 5A, so it has 5 valence electrons. Or carbon is in group 4A, has 4 valence electrons. And sodium is in group 1A, is at 1 valence electrons, and so on and so forth. And then when you want to write Lewis structure for sodium, it's in group 1A, it has 1 valence electron, you put 1 dot here, right? And then for chlorine, how many valence electron chlorine has?
7.
And then you put 1, 2, 3, 4, 5, 6, 7. And now when you write the Lewis structure, you see that this sodium loses an electron, and then this chlorine gains this electron. right? So this one loses, this one gains, and they form an ionic compound, or they form an ionic bond, and then we have sodium chloride, which is the table salt. So just email me if you have any questions, and I'll post the first homework assignment today by the end of the day, and you have like till next Wednesday to work on it. Okay? Have a good weekend, everyone.